Hello there. Welcome to Astraveo's Continuing Education Series, where for our podcast listeners, we talk about mathematics, the physical sciences, of course the natural world, and our personal favourites, astronomy. Now, you know Joseph and I are all up in and about astronomy. We get super excited about that stuff. So let's get going. Welcome to Astraveo's Continuing Education Series, where we look at interesting mathematics, physics, the world around us, the natural sciences, and of course, astronomy. So today we're going to continue talking about area, especially relating to squares, triangles, circles. And we're going to look at two examples tonight that you might see on a standardized test, your student might experience in. Probably for these questions, I've already put two on the board. We're probably talking 9th or 10th grade, maybe. They'll be 15, 16 years old. These appear to be relatively difficult problems, but if we break them down, they're actually quite simple. So we're just going to use our fundamental knowledge that we've already discovered, we've already talked about in the earlier education series, areas of circles, areas of squares, areas of triangles, and there's a bit of Pythag in there as well. So we're going to touch on the Pythagorean theorem that we've already talked about. So let's have a look at the two problems I've already put on the board for us tonight. So they do look complicated at first glance, but the first one is to do with the area of a circle. We've got a couple of hemispheres here, and semicircles, and also a square. Now we're given the area of this circle, and we're being asked what is the area of the square ABCD. In the second one, we're again talking about a semicircle, a hemisphere, but this time we also have a triangle. Now we know the area of the semicircle, and we know the length of one of the arc lengths here, a segment length, but that's all. And we need to work out the distance AB. So both on paper, on the board, on the whiteboard here, look quite difficult. But in practice, they're not too bad, as long as we keep our wits about us, we think about a bit of simple geometry, we remember our area formulae, that's a hard word to say, and also our Pythagoras' theorem. So let's get started. So we'll start with the first one, and I'm going to redraw the image because I did this beforehand, because as you all know by now, I'm not the world's best artist, but I think we should be okay. So it's number one, and we have a square. So I'm going to try my best here, and I'm redrawing it because we need to know some notation. So that already that does not look like a very good square, but I'm going to try my best. So there's one of the hemispheres, the semicircles. There's the other one. Not quite. And I'd like to draw this as best I can tonight because the geometry really does matter. It's much more easy to understand when the diagram is truly representative. So that can't possibly be a square. So I'm going to leave these sides down. Now the circle, the interior circle, touches both of these, just touches both of these interior circles. Not perfect, but it's okay. No. Okay, not perfect, but not too bad. Okay, so let's tidy things up just a little bit. Okay. Oh. Yep, I'm being a bit pedantic here, but I'd like to get this right tonight. I think it will really help. Okay, squeaky pen's come back, say hello. I've missed you, squeaky pen. Okay, there you go. So now we're in business. That's not too bad. So let's look at what we know. This is A. We're going to call this A, B, C, and D. Now the only thing we know is that the area of the circle is pi centimeters squared. So we need to maybe ask ourselves, where do we go from here? That's the only piece of information we have, except that ABCD is a square. This circle is a geometric circle, and these two are geometric semicircles, half circles. So let's think about where we should go. We don't have a great deal of information. So when we first look at it, it's difficult. I'm panicking a bit. But I'm going to remember my fundamentals. If we know the area of this circle, we know we can work out its radius. So let's do that. Let's give this a center. We'll call it O. And we're going to drop this down. And just for the sake of argument, I'm going to call this N. And this midpoint is going to be M. I know it's the midpoint because these two are identical semicircles. So if the area of this circle, we should be able to work out its radius. It's really important. Okay, now we know the area of a circle is pi r squared, where r is the radius. So we already know the actual answer. So pi r squared equals pi centimeters squared. Well, if we divide by pi on both sides to get rid of the pi's, now don't forget, we say this whenever we do our education series videos, with an equation, whatever you do on one side of the equation, you have to do on the other. So we divide by pi on both sides. So of course, they cancel and they cancel. Now, just because they cancel when they divide out, they don't go to 0. A number divided by itself is 1. So we are left with r squared equals 1. And as we've talked about before, the best way to get rid of a square, and something times itself, is to take the square root. So let's go ahead and do that. Number 2. So we are left with r is plus or minus 1 centimeters. Don't forget the units. I always try to remember those. Now, I put plus or minus 1 because if you remember, a plus times a plus is a plus, and a minus times a minus is also a plus. But you can't have negative distances, so it must be plus 1 centimeter squared. So now we have a fundamental measurement in this problem. R equals 1 centimeter. So we know a little bit more than we did before. So I'm going to write it over here. R equals 1. And this was based on area equals 4. No, it wasn't 4. Oh dear. It was pi centimeters squared. Okay, so we're in business. Now we know a piece of information here. Whenever you've got a radius that touches a tangent on a circle, this is from the circle theorem, AD is a tangent to this circle. I haven't drawn it exactly perfect because I can see a small gap. There you go. A tangent to a circle is a straight line touching the circle. The circle theorem tells us that must be a right angle. So we've got yet another piece of information. So we're starting to mass information here just by using some fundamentals. Okay, as all good astronomers, let's give ourselves some space. Okay, so I'm going to get rid of this now. So it'll just complicate things. It will just make us a little bit more upset with all those lines. So now we also, the fact we know this distance means we also know this distance. So we're in business. Now let's give ourselves a measurement here. We don't know the value yet. We're going to work it out, but we don't know it yet. Let's assume this distance from B to M is the R. This small circle has got a radius R. Well, this one also has a radius, R. Well, what that means is, if this is R, have I got this right? No, I don't like the way I'm doing that. R is not a good letter for a square. I think what I want is, that's what I want. Is let's look at the radii. These are identical circles, so they're both the same answer. Actually, that cannot geometrically be true. Hang on. I told you I wasn't the world's best artist. Let's get this right. I told you I wanted this diagram to be right for this question. That must be the radius there. Radius to the touching. Okay, now we're in business. So, let's call this radius R. R. Now, what that means is, this radius, if this is the very center point of BM, this radius here must mean that is R. That is also R. So is that. And so is that. Now, I think you can already tell my diagram is not perfectly to scale, but we know I'm no Picasso. So let's have a think about what this means for our square. Well, this length BC, let's just write it out. BC is 1, 2, 3, 4 times R. We don't know what R is yet. We are going to figure it out, but we don't know yet. So if this is a square, that also must mean that CD, the length CD, is 4 times r. Okay, we're starting to get somewhere now. We have a construct for the length of the square, ABCD. We already know a radius from the center of this circle, ON, we know that, okay? I'm going to write that down here. ON equals 1 centimeter. That's what that means. Okay. So what can we do now? We actually know a few more things. It doesn't look as though we do, but we do. I'm now going to go from O, to M. That's not a very straight line, but anyway. What is the length of OM? Do we know? Not yet, but we can figure it out. We know from M to N, the length M to N is basically 4r. It's all the way down because we know it's the whole length of the square. But we know from O to N is 1. So that must mean this remaining length, that's 4r. ON is 1 centimeter, which must mean O to M is 4r. Ooh, that was a strange r, a strange 4. 4r minus 1. So it must be centimeters. Well, I think everything's in centimeters. It must be centimeters. So the reason how I get 4r minus 1 is because all of this length is 4r. This length is 1 centimeter. We measured it already from the area of a circle, which must mean the remaining length is the 4r minus the 1. So I think we're in business. Now what we're going to do, because I think that's why I brought this up before, a radius and a tangent, the tangent to a radius of a circle must make a 90-degree angle. That's from the circle theorem. That must mean also the same is true up here. O to M would be the equivalent of that, which must mean this is also a right angle. Now that becomes important. We know, I think, yes, that's why I drew it that way, I remember now. Okay, we know this distance here is 1 centimeter. It's the radius of the big circle. So now I think we're okay. We know this length, r. We know this length, we know r. We know this length, and we have a right angle triangle, and we know the base length is r up here. I think we can do some Pythagoras' theorem. I think we are okay. So OM, I'm going to write it over here. 4r minus 1 centimeters. Not entirely sure why I put that in brackets, but there you go. Okay, so yet again, let's give ourselves some space. We always do. That's starting to look a little bit like a complicated diagram to me. I'm starting to get a bit confused. There's lines all over the place. There's R's, there's big R's, small R's, A, B, C, D's. Let's pull out what we really need. We really need this triangle, OM. Well, I'll give ourselves some label here. I don't know. Let's call it Y. We need this triangle, OMY. So let's draw it. Let's just pull out that triangle, nothing else. Now, O is the center of this circle. M is up here. Now we know M has to be OMY must be a 90 degrees because it's complementary to this angle, which is from the circle theorem. And this is Y. Now we know the distance MY, it's R. We know the distance OY, it's the 1 centimeter of the circle, the big circle, plus R here. So this must be R plus 1. And we already discussed OM is 4R minus 1. 4R minus 1. All of these are in centimeters. So that looks to me like a great Pythagorean triangle. So I'm just going to write one more thing here. OY is R plus 1. Everything's going to be in centimeters. Now, it's true, we actually don't know the value of R, but Pythag may allow us to calculate it. So if you remember your Pythagorean theorem from an earlier Astraveo Education Series video, we know that the sum of the squares of the two shortest sides of a right angle triangle, there's the right angle, equals the square of the longest side, the hypotenuse, which is OY, there's OY, radius of 1 plus the r, the radius of the smaller semicircle. So let's see what we get. I'm going to switch to black here. So a squared plus b squared, so it's a, b, c. So the Pythagoras theorem, don't always spell that right, but that looks okay tonight, is a squared plus b squared equals, it's not my world's best c, is it? Oops, c squared. Well, we know a is r squared plus 4r minus 1 all squared equals r plus 1 all squared. Let's see. So that's the hypotenuse. That's the shortest side. That's the second shortest side. Okay, so we're in business. All right, so now see, let's tidy this up a bit. Okay, I'm going to come over here because I used a lot of the board here. Now we've got a couple of complicated expressions here, you might think, but these are special identities. Now, when I was younger, we used to do the eyebrow method, and I will show you that, but these have defined identities. We know that a plus b all squared is, let me get rid of this, a squared plus 2ab plus b squared. And a minus b all squared is a squared minus 2ab plus b squared. Now the reason being is, and in fact I will do the eyebrow method here because I much prefer it. You'll get identical answers. These are set identities. These are just mathematical identities, but we can prove it. So let's rewrite this up here. Let's use a nice little arrow. I'm going to stay in black because it'll highlight nicely on the video. So we have r squared plus, now this is really 4r minus 1 times 4r minus 1. I'm going to have to get rid of my arrow a little bit, equals r plus 1 times r plus 1. Okay, give myself a little arrow. Okay, now here's what I mean by the eyebrow method. R squared. Now, if we follow before I do that, if we follow this method up here, the r plus 1, we should get, this is a and this is b. A is r, b is 1. We should get a squared plus 2 times ab, so it's 2 times that will be 2r, plus b squared, which is 1. So we really, if this is right, we should get a squared, oh no, I'm all over the shop tonight. We should get r squared plus 2r plus 1. So I'm going to do this side first. Now the eyebrow method is this number times this number. That's a plus sign, so it would be plus r. Same with this 1. Plus r, and then 1 times 1 is 1. So you'll get you'll get r squared plus 2r plus 1. Okay, that's good. We get the same answer. So if we use the set identity, we get the same answer as the eyebrow method that I did when I was in school 130 years ago or so. Okay, so that's good. Now, just for convenience, we can use this just to make it a little bit easier. Actually, you know what? I'm going to stick with the eyebrow method. That's how I learned it. Okay, so 4r times 4r is 16r squared. Yeah, okay, that's okay. 16 plus r squared. Now, you have to be careful. 4r times minus 1 is minus 4r. We've already done that one. Now we do minus 1. Minus 1 times 4r is minus another 4r. And minus 1 times minus 1 is plus 1, which is a squared minus 2ab, because that's going to be minus 8r, yes, that's right, and then plus 1, yes. So our eyebrow method matched our second identity, which is good. Okay, so we get r squared plus 16r squared minus 8r plus 1 equals the right-hand side. Okay, we are in business. Whoops, I didn't do that quite right. 16r squared. Okay, so these two together are 17r squared minus 8r plus 1 equals r squared plus 2r plus 1. All right, where do we go from here? Let's give ourselves, I'm running out of room a little bit. I'm going to give ourselves a little bit more space. Oops, okay. So I'm going to subtract r squared from both sides because we have an r squared. So minus r squared minus r squared. So r squared minus r squared is 0. So now we'll go to 17r squared minus 1r squared is 16r squared minus 8r plus 1. R squared, that goes to 0, equals 2r plus 1. Okay. Now I'm going to subtract 2r from both sides because I want to get rid of this. Minus 2r minus 2r. So we get 16r squared minus 8 minus 8r minus 2r is minus 10r plus 1. Those two cancel, equals 1. All right, what have we got here? So now we can subtract 1 from both sides. We get 16r squared minus 10r equals plus 1 minus 1 is 0. 1 minus 1 is 0. Okay, I think we are really close to our answer now. I think we are really close. Now again, that might look complicated because we've got an r squared, and that worries some people. I don't think we need to be worried, actually. So let's do perhaps something that logically, let's actually divide by 2, because these numbers are both divisible by 2. So 16 divided by 2 is 8, so we have 8r squared. 10 divided by 2 is 5, and of course 0 divided by 2 is still 0. Now we have a common factor here we can take out, it's the r. So what we can do is, we can do this. Let's pull out the r. Whoops, my pen's all over the shop. R into 8r squared is 8r, because when you times those two together, you get 8r squared. Minus, because here's a minus, do minus 5, whoops, equals 0. Now let's times this out to make sure we get this, because if we go from here to here, we should be able to go from here to here. R times 8r is 8r squared, magic. R times minus 5 is minus 5r. So we're in business, we've done it right. So we have two solutions. Because this is a multiplication, either r equals 0, we have two solutions. Either r equals 0, because 0 times whatever this is would give you 0, or whatever's in here equals 0. That's better. Let's add 5 to both sides. Don't forget equal sign. Whatever you do to one side, we have to do to the other. Minus 5 plus 5 is 0. We have 8r, 0, equals 5. Divide by 8 on both sides to get rid of the 8. They cancel. We are left with r equals 5 over 8. So we're finished, yes? You caught me out yet again. Every week you catch me out. I'm very impressed. We forgot the units, centimeters. Now we know it's centimeters because the very start of the question said the area of the big circle is 8 centimeters squared. So we know the unit basis of this exercise is centimeters. So that's really nice. Okay, are we finished? Well, no, we're not. Not quite. We're very close, though. We needed to find, the original question was, what is the area of ABCD? Now, we worked out that each length of the square, and it is a square, is 4r. R plus r plus r plus r. Well, we now know r, so we're in business. If each length is 4r and it's a square, oops, the area equals length times width. The length is 4r, and the width is 4r. Okay, with my 4's in two different styles there. One westernized and one European. Okay, so we get 16r squared centimeters squared. Now we know what r squared is. So it's 16 times 5 over 8 all squared, which equals 16. 5 squared is 25. 8 squared is 64. Now we can do that because we can square it like this because there's a multiplication here. If it was a different operand, we may have to think a bit more carefully, but the multiplication makes it easy for us. Now, these are divisible by 2. These two numbers are also divisible by 4 and 8 and 16, in fact. So if you divide 16 by 16, you get 1. And if you divide 64 by 16, you get 4. Good mathematics, well done. So we have, that becomes a 4. We get 25 divided by 4 units. 25 divided by 4, which is an improper fraction. So if you prefer decimals, 4 times 6 is 24. You'd have 1 left over, so it's a quarter. You have 6.25 centimeters squared. It's an area. So we have been able to work out the area of ABCD using just the area of this circle, a little bit of geometry, not too much, some nice calculations, the area of a circle. We obviously just use the area of a square as well. But then once we figured out some nice geometry, we pulled out this triangle, and we were able to then use Pythagoras' theorem to work out this radius, the radius of these two semicircles. But we know then that would allow us to work out the area of the square, the big square. So what that means is we started off with something quite complicated, and we ended up with something really not too bad at all, using a bit of area knowledge, a bit of a circle theorem, a radius touching a tangent gives you a 90-degree angle, and then a little bit of geometry, and then a little bit of Pythagoras at the end. So it wasn't a difficult question if we followed some basic steps. As I say to my children, mathematics is a game, that's all it is. Sometimes the game is difficult, but this wasn't too bad if you didn't get upset, you didn't get worried, you didn't panic, and you followed the basic steps. Some areas, a little bit of geometry, a tiny bit of circle theorem, and then finish off with a wee bit of Pythag, you're in business. Okay, so that was a really nice question. When I was researching this episode for tonight, I found this and I thought, ooh, this is a nice question. I really liked that one. Because instantly, when I saw it, I thought, oh, that looks hard. I wasn't even sure I could do it myself. But then when I sat down with a piece of pen and paper, best friend, by the way, either these pens and a whiteboard or a pen and paper, best friend in mathematics. Draw things out, try out your equations. Really important. Okay, what about number 2? Now, number 2 also looks a little bit difficult. You've got an area, you've got the length of a segment inside a semicircle. That still doesn't give us a great deal of knowledge. So it looks, again, on paper, on the board, it looks like a difficult question. But it actually is not too bad at all. It's one of these deceptive ones that you look at it and think, oh, it's tough, but it's not really. Okay, so I'm going to try and draw it out again because we need to dissect the image a bit. As you know, I'm not exactly David Van Gogh, but we'll give it a go. Oh, gee whiz, that is awful. All right, let's do that again. I need a bit more space. I think that's what it was. I'm going to start with B. I think I was panicking about space a wee bit there. Oh, there you go. That's not bad. That actually worked out well. Left to right suited me a little bit. Right to left suited me a bit better. Yeah, not bad. I fell off a bit at the end. Gravity got the better of me right at the end. Okay, let's see if I can tidy that. Yeah, not bad. Okay, and then what we've got, we have, I think that needs to go up a little bit more. And then we have an interior segment here. Yeah, close. There you go. Okay, and then we were given the center of the semicircle O, and then C, there's D, and there's B. And we have to work out AB. The interior segment is 8 units. Notice there's no units this time. That's interesting. In the area of the semicircle, there are no units given, and the length, there are no units. So this is a unitless question. And we were told also that the area equals, what does it say? 18 pi. 18 pi. Okay. So where to begin? What do you think? It looks tough, doesn't it? Just looking at it, again, one of these questions you might think, I have no idea where to start. I think I know where this is going. Obviously, I did some research on this morning. But again, pen and paper, that's your friend. And that's what I did. I sat down and I drew it out. I was like, it's not too bad after all. We can actually use a little bit of circle theorem here, because AB, to me, looks like a tangent. It's a straight line touching the edge of a circle. Or touching, just touching the edge, which must mean the diameter or the radius, which is what OA is, produces a 90-degree angle. Again, that's from circle theorem. So we know we're given a freebie, actually, if you don't panic too much. I'm going to draw this quite large. There you go. That is a right angle. Now that really, really helps us. Because if you look at that now, in my head, I'm thinking, ooh, there might be a bit of Pythagoras' theorem here. Maybe, we'll see. But we may be able, there's definitely some triangle work coming up. So whenever I see that, I'm thinking, all right, life isn't so bad. Well, we have the area of a semicircle. So I'm suspecting this radius OC, or OA, same thing, we can work that out. We're about to give ourselves a number. I really like that. So the area of a circle, let's do it up here. So the area of a circle is pi r squared. I'm actually going to use a lowercase r, I think. I think partly because it's a small diagram, a capital R seems to take up too much space. Now, don't forget, this is a semicircle. So the area of a semicircle area, must be half of that. Pi r squared divided by 2. Now, but we know the answer, we know the area of that semicircle is 18 pi. So pi r squared equals 18 pi. So, got to be careful. Pi r squared divided by 2. It's a semicircle area, not a circle area. I nearly caught myself out there. Well, the very first thing to do is to divide both sides by pi. I'm going to put a divide by 1 over pi. It's the same as dividing by pi. What that naturally gives us is they cancel. They cancel. So you're left with r squared divided by 2 equals 18. Times by 2 on both sides. Oops, wrong way there. Okay, 2 divided by 2 is cancels. 18 divided by 2 is clearly 36. Now, as we all know, I'll repeat this several times during our educational series, take the square root of anything squared is just itself. Again, whatever you do on one side of an equation with an equal sign, you have to do on the other. So the square root of r squared, of course, is just r. And what number times itself gives 36? 6. So r is plus or minus 6. Now, we know you can't have a negative distance, so it must be the positive. So we now we're in business a little bit better here. Oops. R and R is 6 units. This is 6 units, and this is 6 units. So I don't know about you, I'm starting to feel a little bit better about things. We've got a radius, not quite a hypotenuse. We have a segment inside a circle, but we don't have the distance dB. So we're not out of the woods yet, but we're about to be. The magic is coming now. Now, they teach this in school, I hope, but there's something called Thales' theorem. And what Thales' theorem says is that if you have 3 independent points on a circle, and the distance between 2 of those points is a diameter, the angle for the 3rd point must be 90 degrees. So we can do that. And here's what that really means. I'm going to use a different color pen just to show you what I mean. We're going to go from A to D. Pretty close. I'm a few millimeters off, but that's okay. So we have 3 points on a circle. Now, I realize it's only a semicircle, but effectively it's a circle. We have 3 points, A, D, C. Thales' theorem says 3 independent points on a circle. If 2 of the points make up the diameter, AC, the intersect with the third point must be 90 degrees. That really, really helps us, actually. 90. So we are really in business now, because what we're going to do is we're going to pull out this triangle ADC with a 90 degrees in it. What's screaming at you now? A right angle triangle? My alarm bells are going off for Pythagoras' theorem. This is just perfectly set up for that. So let's just take this triangle alone. Forget all about the rest. And so that's why I love pen and paper or a whiteboard like this, because, let's see if I can draw this properly. I'm not doing the world's best job. Well, yeah, pretty close, not bad. This we know is 90. Doesn't look 90, but it is. This is A, this is D, and this is C. Now we know the length AC. It's 2 of the radii. This radius and this radius is a diameter. So it's 6 plus 6, which is 12 units. We know the distance CD. We were given it in the original question. CD is 8 units. So what's screaming out to us? Pythag. We don't know this side. Because it's opposite the C here, I'm going to give it a small c, give this a small a, and this a small d. Again, the sum of the squares of the 2 shortest sides of a right angle triangle has to equal the square of the longest side, the hypotenuse. So what that means is a squared plus c squared equals d squared. Now we know a is 8, so 8 squared plus, we don't know c, we do need it though, c squared equals d, and d's 12 squared. Well, I hope we all know by now our perfect squares. 2 squared is 4, 6 squared is 36, 8 squared, 64, well done, I like that. Plus c squared, all right, 12 squared is a special number, it's a gross, 144. I know you knew that, I'm okay with that. Okay, again, we've only got one equation, but one unknown. We're going to be able to do this. Let's subtract 64 from both sides. And we are left with, that goes to 0, we are left with c squared equals 144 minus 64. Well, 144 minus 4 is 140. 140 minus 60 is 80. Okay. Now, I don't have a calculator on me, and I'm not probably good enough for my head to work out the square root of 80. It must be close to 9, because 9 squared is 81. It must be 8.97 or something. But that doesn't matter. We can figure it out. So what we're going to do, we'll figure out at least closely. C squared equals 80. Now, I happen to know, I think we all happen to know, that we could break this down. 80 is 10 times 8. Is a 10 and an 8 easily square rootable? Not really, they're not perfect squares. So we need to find a number that's a perfect square. So if you divide by 2, 40 times 2, they're not perfect squares either. Divide 20 by 4, those aren't perfect square, or 4 is, but 20 isn't. 20 is a bit of a pain. Ooh, I think I have it. 80 is 16 times 5. That's a perfect square. So let's do our norm. Whoops, that was a bit of an interesting shape, but there you go. Square root, both sides. Square root of c squared is just c. Now this really is the square root of 16 times the square root of 5. And we know the square root of 6 is plus or minus, of course. We know the square root of 16 is 4, and then root 5, we can just leave as root 5. We can leave it as a mixed number like that. Again, negative distances, of course, don't exist in the real world, certainly on not my whiteboard. And so we have our answer as plus 4 root 5. Again, we have no units, so we don't know them. So I am going to write that in. I think we are getting pretty close to the answer. All right, so we're in business. We've solved that triangle. Let me just check I've got all my numbers right here. 8 squared, 12 squared, 64, 144, 80, 16 times 5. 5 times 10 is 50, 5 times 6 is 30, 30 plus 50 is 80, great. Square root of 4, square root of 5, we've left it as an irrational, improper number. All right, we're in business. So I always like checking things like that because it's so easy to make a mistake. Whenever I did exams when I was in school, I double-checked everything. I really thought it was important to do that. So don't be afraid to go back and check your work. It's a really fundamental process, both when you're an adult, but especially when you're a student. All right, so now we know that this distance is 4 times the square root of 5. How does that help us? Let's have a quick think here. Okay, if this is a tangent, we have another. If this is a straight line, is 180 degrees. Okay, that's the angle really. So we've already got 90. This also must be 90. So again, we're looking at Pythag. Possibly, we've got a right angle triangle. We have one side. We don't know this distance. We don't know this distance. So we're not in Pythag territory yet. In fact, I don't think we need Pythag. I'm pretty sure we don't, if I remember this correctly from this morning. All right, I see where we're going. I see where we're going. All right, I'm going to pull these. We have two distinct triangles. I'm going to pull them out. Okay, let me try and draw these nicely. Have we got enough space? Yes, I think we do. Actually, you know what? I'm going to pull them out here. This now is a DA. Let's go a bit farther down. Yep, that is 90. There's one triangle. Now our other triangle, I'm going to do it very, very close to it. That's pretty close. Okay. Not bad. Not brilliant, but not bad. I think you know me well enough by now, I'm afraid. I can't really apologize for my drawing skills. They're just not the world's best. Okay. Now we know this angle, AC, no, wrong way around. ADC is 90 and ADB is 90. So let's give ourselves our right angle just to make sure. Now we know a couple of distances here. Let's just get these in. AC is the diameter, the 6 plus 6. This is 12. C to D, we were given that, it's 8. And we calculated AD 4 root 5. Well, we have it here too, 4 root 5. So I'm sure you're saying to yourself, how the heck can we figure this out? Well, we know some special information. I may have to draw this a little bit better to prove my point. Give me a second, please. Didn't quite get that right. So it comes down here and down here. There you go. That's a bit better. Oh, I'll learn to draw one day. Holy cow. All right. So now, I think, yes, we're in business. Do we recall what the interior angles of a triangle add up to? Yes, 180 degrees. That's one of the fundamentals of mathematics. There's no getting around that. That sort of comes down from Euclid. That's one of the original tenets of geometrical mathematics. Well, what that means is we can work out the angles here. Now we don't, well, not absolutely. This angle and this angle. So this angle and this part, not the other part, just this part. Let's call this alpha. Let's call this beta. Mathematicians and physicists, astronomers, we tend to use Greek letters a lot for things, especially in mathematics. I'm not really sure why. Well, actually, a lot of the mathematics came from the ancient Greeks. It makes ancient Greeks. It makes perfect sense. So anyway, we use angles are typically Greek letters. Now we know the interior angles here because the interior angles must add up to 180, but we've already got a 90 degrees. So that means alpha plus beta must equal 90 degrees. So these two angles must be. Well, does that help us? Well, it does, because this angle here, that means we're talking this angle. If this is beta, this part here must be 90 minus beta. Whoops, that's not the world's best beta. Well, what's 90 minus beta? We subtract beta from both sides. Whoops. You get alpha, that cancels, equals 90 minus beta. So 90 minus beta is actually alpha. And if these two angles have to add up to 90, if we've already got alpha, this angle has to be beta. All right, now we are in business. I see where we're going. Oops. Okay, this must be beta. This actually has to be alpha. So now we have, by the associated angles, the similar triangles rule in mathematics, we now know that these two triangles are similar because we have two angles, which must mean these two triangles are in perfect ratio with each other, which means we can ratio their sides as well. Because we have alpha and beta, and the angles are both the same, we can do a ratio of triangles because they must be related triangles. They're associated triangles. That's great. Okay, well, we have a hypotenuse here, and we have a hypotenuse here. AB is a hypotenuse. That's great. So why don't we start with this one? And this one must be the angle between... do we need it? No, we need it here. Okay, I understand. So let's start with the angle between the right angle and alpha. Right angle, alpha. So it's this distance, CD, and the way it's written is like, CD is like AD. Let me just check that. 90 degrees to alpha is CD. 90 degrees to alpha is AD. Yes. The hypotenuse is CA, is as to this hypotenuse, which is AB. We're definitely in business. We know this number, we know this number, we know this number, we don't know this number. We're about to get it. Now, the is to symbol, the two dots here, because similar triangles, that's how it's written. CD is to AD as CA is to AB. What this really means is it's a divide by. So, let's do it up here. CD divided by AD is the ratio. Oops, the ratio must be the same as CA divided by AB. Yes, that's right. All right. I think we are ready for the final answer. Let's put some numbers in. CD is 8. AD is, well, there's the root first, 4 root 5 equals CA. Where's CA? 12. It's our big hypotenuse on here. And AB is what we don't know. AB. Whoops. All right, well. So we're going to have to do a little bit of mix matching here. Let me see if I can get this in a good form. First things first, let's multiply both sides by AB. Whatever you do to one side, you have to do to the other. AB. They cancel. So 8 times AB equals 12. Don't forget, this doesn't go to 0. A number divided by a number is 1. Divided by 4 root 5. Have I got this right? I think we're okay. So 8 divided by 4 is 2. There you go. So 2AB divided by the square root of 5 equals 12. Yeah, okay. I think we're going to be pretty close. Okay, give ourselves some space. 2AB over square root of 5 equals 12. Hey, whoops, I've got a spare, don't worry, gravity beat me. Should have gone back to our kinetic energy, potential energy video. Would have been able to work that out quite nicely. Okay, so let's multiply by square root of 5 on both sides. Multiply by root 5. Multiply by, root 5. They obviously cancel. We end up with 2AB equals 12 root 5. 5 by 2 on both sides. They cancel. 12 divided by 2 is 6. AB equals 6 root 5 units. We don't know what those units are. They weren't specified. Is that what we needed to work out? AB is question mark. Yes, that is our final answer. We are in business. Okay. Oh, that was pretty awful. Okay, there you go. So that was a bit more tough. We had to be a bit more careful there. I thought this one wasn't too bad. This question I thought was quite tasty. We had areas of areas of a circle, area of a square. Ultimately, a little bit of geometry, a little bit of circle theorem, and then Pythag to finish us off, and we were in business. This was a little bit tougher. We had to do areas of circles, get ourselves a radius. We had to know about a little bit of circle theorem to get a tangent to a diameter here to give us 90 degrees. A little bit of a circle theorem called Thales theorem to work out the 90 degrees here. A little bit of Pythag to get this length here. And then just a little bit of clever similar triangles work here with some interior angles of a triangle. So this one was a little bit more difficult. We're probably getting up into the realm of maybe AP mathematics here in the US. You're starting to get a little bit more advanced. But then once you were able to figure out that this is probably the hard part, figuring out you had similar triangles, and then you were allowed to do ratios of sides. And then once you'd worked out the mathematics, we were able to get fairly simply to the final answer here. So we were able to work this out. 6 root 5 units. And so we are in business. So that was an example of really if you were to do standardized tests here in the US, sort of MCAS here in Massachusetts, or again, maybe some sort of AP mathematics, again, 9th, 10th grade, maybe, starting to prepare you for some sort of intro to calculus. You're starting to get up there. But on paper, they look really difficult to begin with, but all we were able to do was follow some methodical process of our fundamental mathematics. Some basic areas of fundamental shapes, circles, squares, triangles. A little bit of circle theorem, some basic geometry, a little bit of Pythag, and then finally finishing off with a little bit of similar triangle work. Anyway, thank you for watching.